What is the friction factor in pipe flow analysis? Imagine water rushing through a pipe and feeling some resistance as it moves. That resistance is what the friction factor helps us understand. It's a number that shows how much the pipe's surface and flow conditions slow down the fluid. The friction factor is a dimensionless number, meaning it has no units, and it helps us figure out how much pressure is lost as the fluid travels through the pipe. In fluid mechanics, especially when analyzing pipe flow, the friction factor plays a big role in the Darcy-Weisbach equation. This equation links the pressure loss to the flow velocity, pipe length, pipe diameter, and fluid properties. Knowing the friction factor means we can predict how much energy is needed to keep the fluid moving. The friction factor depends mainly on two things: the flow regime and the pipe surface. The flow regime is described by the Reynolds number, which compares inertial forces to viscous forces in the fluid. If the Reynolds number is less than 2300, the flow is called laminar, and the friction factor is easy to find by dividing 64 by the Reynolds number. This means smooth, orderly flow with minimal turbulence. When the Reynolds number exceeds 4000, the flow becomes turbulent. Turbulent flow is chaotic and affected by the roughness of the pipe's interior surface. The rougher the pipe, the higher the friction factor, which means more resistance and pressure loss. Between 2300 and 4000, the flow is transitional, and the friction factor becomes less predictable. To find the friction factor in turbulent flow, engineers often use tools like the Moody chart. This chart plots the friction factor against the Reynolds number and the pipe's relative roughness. For rough pipes, the Colebrook-White equation is used, but it requires iterative calculations. For smooth pipes, the Blasius equation provides a simpler way to estimate the friction factor for Reynolds numbers up to about 100,000. Understanding the friction factor is essential for designing efficient piping systems. It helps determine the pressure drops, which influence pump size, energy use, and overall system costs. By accurately calculating this number, engineers can ensure that fluids flow smoothly while minimizing energy waste and operational expenses. In short, the friction factor tells us how much the pipe's surface and flow conditions resist movement. It's a key part of fluid mechanics that helps keep piping systems running effectively and efficiently.